In this video, I wanted to have a look at circle properties involving tangents. So our first property says that the tangent to a circle is perpendicular to the radius drawn from the point of contact. So if we draw a radius in and it meets our circle at this point here, if we draw a tangent that meets the circle at that point, then our radius and our tangent are going to be at right angles. Now the converse of that is also true. So the line perpendicular to the radius at the point where it meets the circle is tangent to the circle at that point. So if we draw a radius and then through that point of contact we draw a perpendicular line, then that perpendicular line is going to be a tangent. So let's have a look at what that looks like. So here you can see our circle, we've got our radius drawn and our point of contact is A here. Now, no matter where we move that around the circle, the radius and the tangent are always going to be perpendicular to each other. And that doesn't depend on the size of our circle either. So no matter where it is, it's always going to be perpendicular. Our second property tells us that tangents to a circle from an exterior point are equal. So what that means is that if we have our circle and we pick an exterior point, so we pick this point over here, if we draw two lines from that point that are tangents to the circle, so they just touch the circle in one point, then those two intervals are going to be equal in length. So you can see what that property looks like here. So we've picked our external point A, and it doesn't matter where that A is, these two blue lines are going to just be tangents to the circle, so they would meet at points B and C. And no matter where we put A, they're always going to be equal in length. So it doesn't matter whereabouts that is. The next property to do with tangents says that when two circles touch, the line through their centers passes through their point of contact. So we've got this big circle and a little circle here. We've got a line going from the center of this circle to the center of this circle over here. And that straight line is passing through this point of contact here. Now that rule still holds true even if one of our circles is inside the other. So we've got the center of our big circle here and the center of our little circle here. And if we draw a straight line passing through those two centers, then the point where it meets the circles out here is going to be the point of contact. So it's where the two circles touch is exactly where our line is going to pass through. So what that looks like, here we've got our big circle and our little circle. We've joined O and P, and this point A is the point of contact. And you can see that this interval passes exactly through that point. So it doesn't matter how big our circles are, that's still going to hold. And it doesn't matter if one circle is inside the other circle. It's always going to pass through that point of contact. Our next property states that the angle between a tangent and a chord through the point of contact is equal to the angle in the alternate segment. So breaking that down, what it means is we've got a tangent to our circle drawn along here. Then through this point, we've got a chord drawn. So that's this line up along here. So that chord has to pass through that point. It can't just be a random chord somewhere else on the triangle, in the circle, sorry. So it passes through that point. Now, if we were to draw an angle standing on that chord, so with its base here and here, so we've drawn an angle on there, then this angle here is equal to this angle out here. So the angle between the tangent and the chord is equal to the angle in the alternate segment. Now, whenever you have a situation like this, you actually have two places where it applies. So in this triangle, it kind of looks like the one we just had drawn up. If we draw this up like this a little bit, you can see that this 61 here is between our tangent and our chord, and the alternate angle is this 61 up here. So those two angles are equal. But you can also see, if you look at the other way, that you've got this 87 here, which is equal to the 87 up there. So it doesn't matter where our triangle is or where our tangent is, that relationship is always going to hold true. Our last property relating to tangents says the square of the length of the tangent from an external point is equal to the product of the intercepts of the secant passing through this point. So what that means, we've picked this external point out here, so we're calling that Q. Now if we draw a line from here that's going to be a tangent to our circle, and it meets our circle at this point P, if we take the length PQ and square it, then we'll get the same answer as we would if we took the length QR to its first intercept with the circle and multiplied that by the length QS. So QR times QS will give us the same answer as PQ squared. So just to clarify that with an example, we've got our external point A out here, and we've got these points that are on our circle. So this line from A to D is a tangent to the circle that meets it at A. So if we have a look at the numbers, we can see that AD squared, which is our 3.96 squared, is giving us 15.7. Now, if we took AB, which is 2.18, and we multiplied that by the length of AC, so AC would have to be our 5.02 plus our 2.18 to get that whole length, so that would be 7.2. If we multiply those together, we get our 15.7 as well. So that doesn't matter where this is, that relationship is always going to hold true. Right, so let's have a look at the tangent properties of circles, and just once again we will be going through the proofs to all of those properties in class.